Hi everyone, welcome back to my channel. In the last video, we learned how to calculate time complexity of recursive code by drawing recursion trees and using intuition. But let's be honest, drawing recursion trees for each and every problem is not that practical, especially in competitive programming and interviews. So today, I'm going to teach you a shortcut that helps us to find the time complexity of many recursive algorithms very quickly. This shortcut is called as the Master Theorem, which helps us to analyze divide and conquer algorithms without drawing the full tree. Master Theorem works only when the recursion follows a specific pattern. That pattern looks like this. T of n equals to a into t of n by b plus f of n, where a is the number of recursive calls and n by b is the size of each subproblem, and f of n is like an kind of extra work done outside recursion like merging, looping or printing. So if your recursion looks like this structure, then Master Theorem can be applied. Now let's jump into its core idea. So the core idea of Master Theorem is very simple. We compare two things, that is f of n versus n power log a to the base b. So whatever we found in before pattern we have to apply here, and we have to compare these two, and whichever grows faster decides the time complexity, the final one. So what happens when both become equal? We just multiply by log n. So let's jump into one simple example. This is our last example in our previous video. Here if you see, we have done recursion trees and we have used some intuitions, and again at last we have found the time complexity as big of n. So now here we find the time complexity using the Master Theorem. So here the Master Theorem T of n equals to, this is also n by 2, and this one is also takes time complexity n by 2. So since these are one after the other function calls, we can just add it simply. That becomes 2 into t of n by 2 plus f of n is nothing but some extra work I have mentioned. This is nothing but this one. Here we are just returning based on one simple condition. So this becomes just a constant time. We can write this as big of 1. So this is our pattern which follows the Master Theorem. Now here if you compare a equals to 2 and b equals to 2, and f of n is big of 1. So n power log b is 2 to the base a is 2 becomes n power, this log n to the base n is always 1. So n power 1 is n. So this one is big of n and this one is big of 1. So which one is greater among these two is big of n, and hence this is our time complexity. So this matches exactly what we solved manually in the previous video. So how simple it is, isn't it? So now let's jump to the last and simple example. Here we have t of n equals to t n by 2 plus n. This is the most popular example. We say it as a merge sort. So this is kind of an algorithm where it represented in the form of this Master Theorem pattern. So here a becomes 2 and b becomes 2, and f of n is big of n, we can say. Okay. So now n power log b to the base a would be n power log 2 to the base 2. This become n power 1, so nothing but n. Now if you see, this is also big of n. Now these both are same. If both are same, now we have to multiply by log n to get the final time complexity. So n into log n to the base 2, where we can simply say this as n log n is our time complexity. This is our final time complexity. And this is exactly where merge sort runs in big of n log n. So Master Theorem is not giving a new answer. It's confirming what recursion trees already showed us. So this is all about how to use Master Theorem for the recursion problems or divide and conquer recursions. So the form must be t of n equals to a into t of n by b plus f of n, and then we have to compare f of n with n power log b to the base a, then decide the final time complexity. So this is all about this video. I hope this video really helped you to understand this master theorem. See you in the next video. Till then, happy coding. Thank you.